So thanks for coming to the Temporal Graph reading group on September 21st. And today we are very excited to host Karamjit, who is the author for the Temporal Graph Learning for Financial World Algorithms, Scalability, Explainability, and Fairness. So a lot of interesting aspects. And Karam is currently the director of artificial intelligence at MasterCard, where he focuses on creating AI-driven products in the payment space. With 11 years of experience spanning various industries, he holds dual master's degrees, including a Master of Technology in Computer Applications from IIT Delhi and a master's in mathematics. He has authored over 20 publications in AI and ML conferences and holds more than 15 patents. Karam has achieved recognition through accomplishments like securing the second rank in CIKM 2020 Analytics Cup and winning the IEEE VGTC VPG International Data Visualization Contest. He has also contributed to data science conferences and workshops as part of program committees and organized the MU-FIN workshop at CIKM 2021 and ECML PAKDD 2022 and AAAI 2023. And let's give the mic to Karam to start the talk.
Thanks, Andy. Thanks everyone for inviting us. So yeah, so I think we met on one of the conference. So it was a workshop you guys have on the Neuro app. So we are glad that we have an intersection. We are working on a very similar topics. Our topics are of interest. So this particular presentation will I know all of you came from the research background and very much up to date on what is going on in this world. So I will not dare to, present this from the research side or from the technical side. I will stick to the industrial side. My screen is up.
Yes, we can see the slides.
Okay.
But we can also see the next slide. Okay, I think this is the correct screen. Yeah.
Okay, just hold on a minute. Wait, okay. So, like I mentioned, I will stick to the industrial side of the world, that how this particular presentation. So this was what we presented in KDD, and eventually this was the same. We took it forward. So temporal graph learning for financial world. In general, graphs are very important for us. For MasterCard point of view, it resonates very well for our data, our kind of data, and which we will talk about. So what we will do is we will go through this agenda today, and where we will have a foundation, like we'll go to the basics, like what is graph neural network, which I'm assuming most of you are already aware, and why the graph embeddings make sense to us, and what are the graphs, how the graphs are in financial world. And then we'll move on to that our kind of world, where how do we formulate transactions as graphs, and what are the different applications. So what are we trying to solve that's more important from our payment space, how we are trying to leverage graphs, what are the different applications, and then what are the different challenges. So what are the requirements we have, and where we believe that where we are right now in terms of what are the challenges which MasterCard or other industrial companies in the payment space looking forward to have them resolved in the current GNN world. And we will talk about, again, from the fourth section, I will go high level from the point of view that what are the different state of the art in GNNs and how they are relevant to us in terms of we look at the four worlds. We look at the scalability, which is important to us. We look at the temporal behavior, which is very important to our data. Then there is a bipartite graph world, which also resonates well with us. And then there is a fairness and universal graph embedding. So fairness is also from the industrial point of view that how GNNs are fair, and the bias and fairness in GNNs is also important. So overall, we'll try to cover the all aspects of it, that how uh, different requirements, all these things which I'm talking about, the scalability, temporal, bipartiteness, and the fairness, these are sort of the requirements for us to use GNNs in the financial world or in the industrial world. And then what we believe is the state of the art right now, it's little stale PPT, to be honest, because this was in 2022, and as you know that the world is moving so fast, especially in the AI space. And I'm sure you guys have much more context and the latestness on the what papers are there. So we're looking forward on this presentation. I'm really looking forward to get some references from you guys also, if you believe that these are the kind of papers and the research which can help us and move forward. That will also be really appreciable. Cool. So let me go.
So yeah, there you go. So like we discussed that we wanted to go through like what is neural network, what is graph embeddings, and this is like sort of motivation for us. Like I said, uh, the the people in this call are much aware of this, so I'll go through quickly. But why like this resonated well for us, that the what first of all, like what is embedding? So if we have to solve a problem like this, which is 5 plus 3 minus 2, I know that all of us solves it very easily, right? That's how we are embedded in our brain. We know how to do the addition, subtraction, division, and multiplications and all that. But if we have to solve the same problem with from this language perspective, which is we say that okay, if you subtract the man from king and then add a woman into it, then what will be the answer? And then I don't know if you guys have seen this example, but you can type in your answer if you want to guess it. Similarly, if I wanted to subtract the today from biking and add a yesterday, then what would be the answer? And then the third one. Now, inherently, this problem is obviously we cannot solve it, but as we all know, the embedding world has this is the answers from the embedding world, that if you subtract the man from the king plus and add a woman, it becomes queen, and so on. But why we are able to do it? Because what embeddings does is that are able to map the words in give a numerical representations to the word. And anything numerical, we can do all the mathematical operations, but anything in English language or natural language, we cannot do that. So the embeddings are nothing but it maps the words to the numerical representation, and those representations are intelligent enough so that the similar words, the words which are being used together, they come closer, and there is a context in it. It learns a context, and obviously this space has evolved tremendously. You started from the simple word embeddings, and now we have world has moved so quickly over it. So what this is our motivation. So why I'm sharing it, that this sets a motivation for us, because for Mastercard we also have, we don't have the English words. What we have is we have entities. Now, what are our entities? We have entities which are the cards, which are the users, and we have entities which are merchants. We have, and there are so many card attributes, the user attributes, and there are so many uh, y- uh, the merchant attributes. So when you are taking your card and you're transacting at certain merchant, then both of the card and the merchant are entities which have so many attributes along with it. And then our goal is that what if we map these, what if we learn the embeddings for every entity in our network, such as the user and such as the merchant, and then map it so that those in the embeddings are intelligent enough to learn the context and to learn that which two users are similar to each other. Sorry, my the East Coast is getting cold, so I have some running nose. So the idea is to learn the richness which is unique to MasterCard, learn that the context of the cardholders, they learn the context of the merchants, and then embed that information to for the downstream applications. Like very simple example, like let's say that there's a cardholder which is doing the transactions at various different and merchants, such from Nike to Ralph Lauren to Netflix and all, and Starbucks. And that Starbucks, we know that let's say it is in the certain campus, and then those cardholders, there are so many cardholders which are doing the transaction at uh, in that campus, and this particular card is also doing in that campus. And then there are card holders which obviously doing the transaction at Uber, because as you know, in the student life, the cab is a very common function. And then we know that if the the cardholders which are doing a transaction at that campus are also doing a transaction at certain insurance sites. So what we can do is we can actually use this context. So we can use that 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 if you are doing a merchant going to a merchant one, and then what other cards are doing on that merchants, and then what is the change. So if you can see in the graph world, it forms the sequences, right? That the iterations, we call it the graph at a layer number one, the graph at layer number two, and graph at layer number n. So using this information, we can basically narrow down that what is the context of this particular card holder, and the goal is to learn the intelligent embedding for this card holder, so that, like I said, that use that embedding for solving the downstream applications. So, but why graph? Like, this is the one thing which we also had to talk internally. So as you know, the most enterprise data sets are structured data sets. Though we know that the AI has taken a huge leap in the area of text, in the area of vision. Wherever there is a image data, video data, or uh, there is a uh, the unstructured data, we know uh, that AI has achieved so much, especially with the recent transformers, the generative AI. We see that how world is moving. But having said that, from the enterprise perspective, from the industrial perspective, many industries still have a structured data. When I say structured data, it's the rows and column. Let's take an example of Mastercard. Mastercard has a data which is in the rows. Every row is a transaction, and then let's say if every row is a transaction, and then what you have is the columns as the attributes of those transactions. Or if you believe that if you want to make a card holder as a row, then the features of the card holder is becomes a column. So then it becomes a structured data problem, and then you know that the traditional machine learning how it works. So what happens in traditional machine learning, this is what we able to capture, that this we just able to look at that this user one, which is a card holder for us, and this M1 M2 is a merchant for us, that what transaction this card holder is doing in various merchants on various merchants, and then we are able to model that only. That's what traditional machine learning algorithm does for us. It able to model this part of the graph only. But what 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 the what if I convert this thing into a bipartite graph, where I able to bring in more users and all the merchants, and then it becomes this. Now we are able to solve the problem, which is much more context aware. In the traditional machine learning, we know that the fixed length vector could be very large. Like, we can create as many features as we want. Information is limited to the first order, and it does not capture the context of other users, other merchants. Whereas a graph can give you the fixed length vector, like in the form of embedding. You can have a features which is in the form of embedding, and the information, the representation is much more enriched because it captures the context for the user emerges. So this is why the graph matters, and it makes sense for our kind of data. And please stop me anytime you have any questions, raise a hand. Okay, let's make it interactive rather than one way. So, like I said, graph neural networks, and I'm sure you all of you are aware of it. I'm just gonna go quickly over it. That what is the representation of graph? Graph basically contain the three aspects. One is a node, one is an edge, and one is a connectivity. So node can have their attributes, edges can have its attributes, and then adjacency matrix is basically that how nodes and different nodes are interactive with each other. This is the graph for our world, a very simple graph, though we can actually have a multiple types of graph, but this is the more of a bipartite graph where you have a card holder, and you have a merchant, you have a and then you have edges. So cardholder does a transaction on the merchant, and then cardholder has its own attributes. What are the attributes of cardholders? The attributes of cardholder is that we can create some like what kind of card it owns. Is it a gold? Is it a platinum? And then we can look at the historical feature, that what is the average amount this card spends, right? And then what percentage of transactions are contactless, or what percentage of transactions are uh, uh, cross border. This is the cardholder features. Then merchant features are pretty straightforward. What is the industry it belongs? There is a super industry, sub industry. What is the average volume with this merchant process and all that? And then there is a transaction, there is a node edge feature, because now cardholder is transacting at that particular merchant. That means that now uh, you have a different uh, date, that this particular transaction, when it is happening, what is the amount? Is it a contactless transaction? Is it a chip based transaction? Is it a cross border? Is it a domestic? uh, there are so many features which you have at a transaction level, which you can put it on the edge. So this makes our graph very, very rich.
There's a question from the chat you might want to address now.
That's a good question. So the question is that you have a different type of nodes. That is one type of cardholder type, another is a merchant. Yes. So we definitely have a heterogeneous graph if we put it in that language. Because we have a one type of nodes which are the cardholders. We have one type of nodes which are merchants. These two different type of nodes have a different type of attributes, as you can imagine. So and then so do you just have all features available for all nodes and leave some empty? Yes. So like we do follow, since it becomes a heterogeneous graph for us. So we do follow the techniques which works for heterogeneity, where sometimes we create the equal length of features for both sides and then try to leave it empty. But there are some advanced algorithms which help us to solve the heterogeneity in the graph. Cool. So there's so many slides in this one, which were there in the three hours of session. So I'll just try to skip as quickly. So now let's talk about the main part, like what can we do on the transaction? Now you have already seen that how the transactional graph looks like, right? So now what we can do now in the machine learning world, let's say I have to predict the next edge, right? Like I just have to predict, if it is a temporal graph, I want to predict the next edge. Now, what does this problem becomes for us? Now we can actually predict the next transaction, right? Imagine how powerful it would be that if we can predict that where will the next edge, if we have a dynamic temporal graph, where will the next transaction will occur. Now, but then we can solve a lot of problems by doing predicting the properties of the next edge also. Like next edge about what? Edge is a transaction. what is our next merchant. Like we can, if we can predict that which merchant you will do a transaction next, what amount you will spend, what time you will do, whether that transaction will be card present or not present in contactless. So all these becomes very, very important information, and we can solve a lot of pain points. The very simple problem, let's say that our model says that this is the most likelihood transaction, this is what is going to happen, and then the transaction which is happening is way away from it, very away from, so we can use the anomaly detection to say that, oh, this might be a fraudulent transaction. So ultimate goal is to solve the pain points, right? So yeah, by using this kind of predictions. Then if you can predict the dying node, let's say that that becomes the attrition, right? Like the dying node is like the card holder is not spending any money going forward, or the merchant is not in the system. The merchant can be gone out of the system because of various reasons. Sometimes there are fraudulent merchants which comes into the network or system just to do the fraudulent transactions, and then they went out of the system. So that becomes the predicting the dying node. And then you can predict the properties of the of the node level predictions, whether if the node is a card holder, whether this card holder will have a non-sufficient funds, whether this merchant is a crypto merchant, whether this merchant is a breach merchant, or this card is a breach one or not, whether this card is a fraudulent merchant or fraudulent card or not. So all these things you can do a lot of stuff by doing this thing by doing the properties on the nodes. So this was the kind of some examples which we can solve by using graphs, and these are just I would say that a high level, which we can do a lot more stuff than that. But I wanted to give an idea that why it what kind of problems which we can solve. But there are challenges which we believe that currently exist in the research community. The GNNs are evolving. They are not there yet that they can just be a plug and play. One of the challenge which we have, and it's not an or. I think for company like Mastercard, all of these challenges which I'm putting out is the sort of an and situation. So what we have is we need a scalability. So as you can imagine, so we have actually in the overall globally we have billions of cards and then millions of merchants which are on our network. So even if you have to make uh, uh, a simple bipartite graph, it will be like million into million adjacency metrics. If you try to solve it with an algorithm like a GCN, you can imagine that we will get into the situation of that the scalability is the first thing, and the edges are billions. Like there, Mastercard is processing 1 billion transaction every day. So you can imagine the scale that every day there are billions of edges which are getting formed and going away, and the next day again. So that's the level of scalability which is basically using. Then there is a temporal aspect to it. You know that the rich information is in the time domain. Now think of it this way. Let's say that you have done a transaction at a U-Haul, right? We all, I think most of us from US, and we know that what is U-Haul, right? So if we have done a transaction in U-Haul, now, your probability of doing a transaction at Home Depot after U-Haul is very high, or it increases significantly, because U-Haul means you are most likely moving, and when you're moving you definitely need you will go to Home Depot to do some other stuff. And I am this I am example, I'm bringing it from my personal experience. I recently moved, so obviously I book a U-Haul and I book a Home Depot. I went to a bunch of stuff which is required to that. So that is the temporal aspect. Now, if we know that if you bought a Tesla, then the probability of you going to gas station now decreases, right? If you bought a Tesla. But if you bought something else, let's say a Toyota or some other vehicle, then the gas station probability is high. So these are the small examples which are just first order, but what graph can actually do is they can actually learn this in more rigorous way and advanced way. So I can see, Andy, you have raised your hand. So yeah, please ask your question if there is any.
Just a high level question about how you handle the data. Like you mentioned that there's like a lot of like
Yeah,
that you have like billions of edges. So my
yeah.
question is like from a high level point of view, should you be training with, let's say, all the data you have from all the countries in the world and learn a super like foundational model like those for the language, or should you separate them, like to say like transaction data from India, from Canada, from US, and separate to a specialized model to deal with the specific demographic?
Yeah,
Like,
that's a very good question. So most of our models are regional based. As you can imagine that the regional spends, the properties of the spends in a particular region, or I would say even a country level, are very different. The people who are spending in India are very different. The people who are spending in US, the kind of spends they have. So what we do is that, like, for countries like US, we definitely have a US level. We usually have a US level models, and then for the regions such as the Middle East, right? So then we do try to do a Middle East level region, and then we further segregate. Then for us, there is a regions, and then there are divisions, and then there are countries. So we try to do region and the division level. So we sometimes we go to country level, but divisions sometimes, even Europe for us is like in a certain separate divisions which have a similar demographics and all. So we try to do that to make sure that it captures those aspects. But what we are trying to do is that you can call it as a local context, right? So what we are trying to do is that we wanted to bring in the local context, and we wanted to join that with a global context, because as you can imagine that if you are traveling, there is a cross border transactions as well, right? So someone from India is going to Europe and vice versa. So that context is come from the global one. So we wanted to bring that, and that is where obviously there is a challenge to bring to train such a large model and bring in the global context. So like then as there was a question on that, the other aspect for us is the graph for us is not homogeneous. Every node has a different set of attributes, so there is a heterogeneity for us, which basically, and then the other part which is required from the payment space is the inductiveness. So the graphs which we deal with is inductive, and from the graph language, as you guys know, that there's a transductive and there's an inductive. So inductive is that when the addition and the deletion of nodes are keep happening, and they are dynamic graphs. So a simple example is that every day the banks are issuing new cards, so a lot of additions are happening every day, and then many of these cards are getting expired every day now, right? We have as you know, every card has like 3 to 5 year of expiry date. So the cards are getting expired and the cards are getting added, and cards are getting it right also, like they stop spending. So there is an inductiveness. So this particular four sets really forms the graph used for our world, that we need to have these all four properties. Like I said, it's not an or condition for us, it's more of an and condition for us, that all all are four important for us to actually leverage graphs efficiently. So in the interest of time, so then I'll go into the each aspect of it. Like there are some papers which we used, and there's a research which we are using as a base and then building over it. Our teams are spending a lot of time and work in leveraging it. So as you can imagine, we had to actually use the this one for from various angles. We had to solve the scalability challenge, not just from algorithms, but also from the infra side, right? It's not just that if you have the algorithm which can give you the scale, but you need to have the backup with the machines. And then there is a temporal aspect, there is a heterogeneity and all that aspect which we are talking about here. So scalability graphs, so there are some uh, interesting and good papers which came, uh, which you can see. There's a PyTorch big graph, there's a Cleara, there's a Sign, and I'll briefly talk about these papers. I'm sure you guys are aware of it. So PyTorch big graph is basically a distributed system for learning graph embeddings for large graphs. So in a nutshell, what it does is basically partition the graph into multiple parts. And then as you can see that and then each part fits into the memory into a single machine, and then it trains the each part of each into separate model, and then basically after training it merges the embeddings of each part. So it works. It though the it lacks intelligence, or the I would say that it lacks the context which we wanted to add, but it definitely gives you the handy embeddings at such a scale because of this distributed nature which it works for. So this is just a picture from that paper. And then there's another interesting paper, very simple one. I would say the Clara is very simple paper in a sense that it works at a scale level. What it does is that uh, it initializes the embeddings to a random values, and then it just takes on average of so each node embedding is the set of the average of the embeddings of its neighbors. So it keeps on taking the average of its neighbors by weighted by the edge weights, obviously, and then the embeddings are normalized to across dimensions. So it's simple, very simple, very handy technique. Just randomly initialize and then keep on taking an average by the and weigh by the average weight. So that way it works, like I said, but it might not have a very huge learn the richness might not be an issue. It might be an issue, but yes, all these method definitely works at a scale. Then this SIGN sign paper, scalable inception graph neural network paper. It is actually again this is a recent paper. Again, there are like I said, this is a little stale PPT. It is designed to address the challenge of scaling graph, right? So it does not require graph sampling. So one of the main thing is that it does not do the sampling, which makes it more efficient and scalable than the other GNN architectures. And it is able to show that. Honestly, we haven't tried that yet, but it is able to show that it works on the 100 million nodes to that level. It is able to actually train the models and train the embeddings. Moving on to the temporal graphs. So these were the bunch of scalable graphs for us. So moving on to the temporal graph of the world, there's a huge work going on in the temporal graph, and as I was there in your workshop, very excited to see last year, and I'm looking forward to do it this year. You guys are going this year also to the same location, NIPS?
Yes, so we'll have the workshop again. And since we're talking about this, I will plug an ad here. If any of you want to submit to the workshop, the deadline is October 3rd. So and
Oh,
then
awesome, good to know that. Yeah,
uh
definitely. A lot of our work is focused on this part. I think it resonates well. Where is it happening this year? Neuro
it's
IPC?
like it's still at like New Orleans, the same place.
Same place. Oh, okay,
Yeah.
interesting.
I think they do the same place for 2 years and then switch it up, but I'm not.
Yeah.
Yeah.
The only thing they need to do in that place is that have some uh, public transport inside that place. So it's so you have to
That's
walk
so
so
large.
that's so large. You have to just walk and walk. So
Yes.
coming back to this temporal graphs, this is the kind of work we are seeing, which is happening, which we are leveraging as a base. Again, we'll go quickly over it. There is the GNNs with the discrete time, then there is a continuous time, and there is a temporal point processes. There is a evolve GCN, GCN LSTM, GCN GRUs. Then in the continuous time, very good papers. I would say that TGAT is obviously a very popular one. TGN is a popular, and then we have seen trend paper is actually seems to be working very well. So these are some interesting papers for us. So evolve GCN, I think many of you obviously aware of. These are dynamic graph representation learning. It's sort of a, like the name suggests, it evolves the GCN, right? So it addresses scenarios where the graph evolves over time. It basically learns for dynamic graphs, and and traditional method of relying on the node embeddings. We know that if the graph evolves, then the traditional method doesn't work, and it adapts a GCN model along with the temporal dimension, and without relying too much on the node embedding. So the proposed approach in a nutshell, it uses the RNNs with a combination of GCN parameters, and it allows it to handle a scenario where the node set changes frequently, which is very relevant to us. We know that the node sets are evolving for us, especially the card side of the world. The merchant nodes are not evolving that frequently as compared to the card sets. So this is the rough architecture. I'll just skip it. Then there is a GC LSTM, pretty much similar, but trying. So those all these papers where what they've done is, in a nutshell, is that they pick up the traditional GCN kind of architecture, and then add a RNN part of the world. Like GCLSTM is combination of as you can imagine, it basically introduced end-to-end deep learning model for dynamic link prediction. The model was actually to predict that link prediction. So as you can imagine, that the edge prediction to problems which I talked about. So it combines that graph convolution, which is the GC part of it, and then to learn the network structure, and then LSTM to learn the temporal feature of the network. So this aims to handle the high dimensional, time dependent, and the sparse structural sequence data. In the continuous time, as there is a very good paper which we do definitely leverage, and this seems like a good paper, which is a TGAT. Uh, TGAT is nothing but a temporal graph attention layer. So the challenge is, we know that the node embeddings should not just only capture the topological structure, but node features, but also incorporate the continuous time, right? So there are three aspects to it. There is a node features, there is a uh, topological structure, and then there is a continuous time. So this is the paper which tries to tackle all. So basically, it introduced the concept of temporal graphs, temporal graph representation learning, which should be inductive, and it allows the generation of embedding for unseen nodes efficiently. So it definitely tackles the inductive part of it, especially the for us. You can think of it that the card got issued yesterday. It got introduced into our network. It hasn't done too many transactions, so it's like a cold start problem for us. So that kind of problems can be solved from here. And then this paper basically combines the self attention mechanism with the uh, functional. There's a novel approach which they introduce, a functional time encoding technique, which is derived from the harmonic analysis, which I can tell you about the high level. But like I said, you guys are much more evolved in this topic, so I will not be try to be an expert in this one. Then there's a TGN. uh, TGN is another very good paper in this space for temporal one. Uh, TGN introduces a very generic and efficient framework. It is more than the algorithm, it is a framework which they introduce for learning the dynamic graph representation as a sequence of time events. So they basically combine multiple modules, and what they introduce is like, in a summary, they have like 5 modules. Uh, with these modules, memory module and the graph-based operators to outperform the previous approaches, such as which we discussed. So as you can see, there is a memory module, there is a message passing, there is a aggregator, and then the memory updater, and eventually the graph embedding. So it uses memory to store the node histories. It compute the messages to update the memories based on the events, and then employ various strategies to aggregate this message efficiently in a nutshell. So their main key innovation is in ability to produce node embeddings that adapts from the long-term changes and inactivity in the graph. So there are limitations. There are papers which are, I think, like I discussed, that there are papers which works for scalable, but they are not able to handle the enriched information that we have. Then there are paper which touches upon inductiveness, but then again they don't work at scale. Then there are paper which touches the temporal aspect to it, and inductiveness, but again does not handle the scale part of the world. So there are limitations. And then there is a one paper which is again very interesting, not so popular surprisingly, which is the trend paper, which we did find it very useful for us. uh, it basically introduces a framework for temporal graph learning. It does leverage the Hawkeye process, which is based on GNN to capture the evolving dynamic graph. So it trend this work is inductive, so it definitely handles that inductiveness, that is it can handle the new nodes at test time. Then it uses the Hawkeye process to capture the exciting effects between the events, and then considering how past events influence the future ones. So it looks at the, it call it exciting effects. So it looks at the temporal aspect to it, right? And then I think event and node dynamic, it talks about that. It introduces the concept of event and node dynamics. So event dynamics capture the uniqueness of individual events, and then while the node dynamics governs the occurrence of event collectively based on the characteristic of nodes. So definitely it is exciting work which we looked at. It also talks about that how TGAT and TGN model can deal with continuously evolving graph, but they might fail to explicitly model a exciting effect, which is talking about exciting effect between the sequential event holistically on the entire graph. So more of the global information it misses, which it talks about the TGN and the TGATs. Then we had a paper in a T graph where we actually tried to combine the TPPs with the GNNs. Very simple paper in a but very relevant conference for us in the financial conference, where what we try to do is we look at the embeddings from the TPPs and then the GNNs, and then we try to combine. The idea is that we wanted to learn the structural behavior as well as topological behavior as well as the temporal aspect to it, and the goal is to classify the labels and the nodes, that is that this particular card is fraudulent or not, the fraud versus non-fraud problem. And at the last, as you can see, that I was telling that the bipartite graphs are also very, very relevant to us. As you can imagine, which I showed you, that we form the bipartite graph naturally between user and cardholder. So yeah, Andy, you have a question here?
Mm. Yes. So very exciting paper, and I haven't seen it before. But I'm just curious if you like, what are the data set that you are testing the like the fraud user detection um, for?
So yes, that's a good. So unfortunately, I think the payment space, the financial world lacks the open source data sets. So what we do is, and we have our own limitations to publish papers on the real data sets. So what we
Right.
do is we take the dual route. We do test papers on our internal data, and for publications we do simulate the data as close to the real data, so that you know that there's a lot of work in terms of the data simulation, where especially in the GANs, where you can actually maintain the distributions. So that's the main approach we take in our publications, that we try to simulate the data from our real data for publications, and obviously for internal we do use the real data which we have at scale.
Yeah, I think for temporal graphs, especially for like node classification, which is kind of like the like
Yeah,
like detection task,
yeah,
there's huge problem with like lack of large scale data sets.
yes, absolutely.
Data
Yeah,
sets, but it's like it's very difficult to get the precise timestamp or the correct
yeah,
label for the nodes. Um, and then if you, like I understand that like it's very difficult to release like the industry data set, but I think like like what you said about like having a synthetic data set that are very close to the real world data set will be actually
Yeah.
very helpful for the community.
Yeah. So
Like
so I think the industry is evolving. We are also evolving till what when we start. As you can imagine that the industry leadership, you need to, it takes a while to explain the usability of the releasing the data sets to the outer world, because it has a long-term effects, as well as that making sure that we are following the compliance and privacy and everything, so that we unknowingly does not send out the data which you should not. To be honest, we are working towards this. For us, is the next step is obviously release some data to the community, so that which is close to our real data, so that we can also start leveraging the research. We are parallelly, we are also partnering with the universities, global universities, and the professors, which who are actually uh, meeting us weekly to guide us uh, to the research side of the thing, so that the data doesn't go out, and their students comes to Mastercard and work with us as an interns. And also all these efforts are going on. I think we'll get there. We're not there, but we're definitely heading to the direction where Mastercard releases some sort of simulated data for the community, so that we can start leveraging the research for the outer world.
okay, sounds good, and very like excited to see the data set like in the
For
future.
sure.
And
Yeah.
then if you have the data set like if you can share with me or like in the Slack or like or by email,
Yeah.
something that would be very nice.
I can. So I think there are few data sets which to be honest, I was working in the research side of the world. I was like 1.5 year back, but it's been a year when I moved to US. I'm now more on the business side, product side of the world. But I'll check with my team in India, who recently, have published a lot of papers in the top conferences. So let me check if they have, recently released some data, or what data they are leveraging. So I can ping you those data sets for sure.
Okay, perfect. That'll be very.
Just one quick note, maybe Andy, you can also advertise the TGB project here.
Yes, I do want to, but I don't want to take too much away from the presentation. So just very quickly, like the reason that I was very interested in the like in the data set is because so like me and Pharma and other collaborators are like working on a very large scale benchmark for temporal graph learning and trying to standardize and trying to measure like the model performances on both like link prediction
Yeah.
so, like and like the no classification task. But the
Okay.
main problem with the no classification task is that it's very difficult to find like good data set with the correct
Yeah.
label, timestamp, and these kind of things. So like if you know some of like some data sources,
For
that would be
sure.
very nice too.
Yeah, and then like I said, I think it both ways. I will also request you guys. You guys are very much connected to the research world and up to date. So if you feel that you have seen what we are trying to solve, right? If you feel that any of the work, apart from to you what you are trying to solve, which we are looking forward, you feel that this is something which we can explore. Feel free to ping me the papers and all. Okay. So,
Okay.
but we'll definitely. I think you guys are definitely working in the area which is very very close to us. We have a huge intersection. I will bring it up with my with Nitender, who could not join today. He leads the the AI garage world, which is mainly focusing on this research world. So he is a lead of that. So he's actually leading a lot of partnerships with universities across the world. So probably there's something partner future partnership we can also have, especially since you guys are trying to solve the similar problem which we are solving. So
Okay.
we can probably figure out some way of sharing the data and leverage your work. So let me talk to him also about this, and looking forward to that partnership.
Okay. Okay. Sounds good. So let's take the discussion offline and
Yeah, for sure.
for the explanation.
Okay, so for bipartite graphs, like I said, I think you guys have quickly seen it. So there are a bunch of papers which we recently leveraged, and like I said, this has evolved quickly. There's a Baijai paper which is very interesting, that it uses the mutual information maximization technique. The idea is that it uses the local context as well as the global context, that which we were talking, that how we need the local as well as the global context for learning the Brett embeddings, and a lot of our graphs are bipartite between user and merchant. So it definitely uh, does have a good work in that area, right? So it basically developing a local and global informatics objective that leverage the both node types using global prototype representation and local subgroups. So okay, I think we are right on time, and I unfortunately have a meeting. So I'll just quickly I'll share this deck with you guys. So again, the last topic for us is the fairness. As a Mastercard, is very important that whatever technology we use, that we keep a check on the bias and the fairness. And there are some papers which does talk about that how GNNs can be a little bit more unbiased than the traditional algorithms, and especially since they are evolving space, a lot of work has not been touched upon. So any work which happens in this area is also, we keep an eye on it. Whether we also have a paper in it, like in the PAKDT and all, where we able to establish that what are the definitions of fairness in our world, and how we can use leverage check GNNs whether they are fair or not. So there's a fair GNN, very popular paper in this one, and then this is our paper which got published in PAKDT FLIB, which is fair link prediction in bipartite network, where we actually did solve the link prediction problem in the bipartite graph, but we also measure the fairness of it, and then we show that how the existing algorithms are not doing very well on that part. So yeah, so yeah, like I said, this paper was we compared the traditional GNNs, the fair HIN, fair GNN, and then the FLIB, and then we measure these fairness metrics which we are able to show. And to sum it up for us, like I said, the open problem for temporal graph in the financial world is that uh, something which is, when I say elegant representation, or you can say enriched information for dynamic, heterogeneity, and temporal behavior. So these three things are the key aspect to it. That there's a evolving graph, there's a heterogeneity in the graph, and then there's a temporal behavior. And and I think the new modeling techniques, as opposed to we build over the traditional ones. And handling the cold start problem is also very important. Like I said, the card got issued yesterday, it didn't have any so many transactions, but we obviously need to know if this card is exposed, or if the card is relevant to be fraudulent. Even the same merchant problem, the merchant got introduced in the network, onboarded, we want to know if it is like a fraudulent merchant or not. And then computational complexity is obviously the scalability aspect of it, which we talked about. So yeah, this is it. Thank you so much. And if there are any questions, feel free to reach out to me. Andy has my connect. I'm on the LinkedIn. You can find me with the same name, and reach out. And looking forward to work with you guys. And I will definitely ask my team to look into your workshop, and if there are any papers we can submit.
And then, yeah, so maybe we'll see you in person at the workshop. And
Yeah, most likely. Most likely, yes.
thanks,
Definitely like to stay up to date on the work, and I think your workshop has a very good venue to stay on the up to date of what is happening in this world.
thanks. Glad to hear that. And yeah, very nice talk. And you can share the slide with me. So I will put
Yeah,
it on the reading group website, so like people can check
sure.
offline the papers and the references. Yeah.
Yeah, cool. Thanks. Thanks.